Hello, guys.
Hello, Professor.
Hello,
Hey.
Professor.
Hello, how are you?
I'm fine. How are you?
I'm good. Seems we're getting back to winter, like swinging.
Yeah.
Yeah.
Professor, I have problem to install TensorFlow. What should I
Okay.
do?
So same problem. Same issue when you install the pattern.
Pattern? No, it's different. For TensorFlow, is when I install and it shows like couldn't find the maybe properly version for the current environment or something like that.
Oh.
And then I studied the TensorFlow website, and I think they have a lot of ways, and I try to use some of the ways to install the version 2.10 something or 2.3.10, and but even I install correctly, and I couldn't run the code. Like for example, I run the code to check the version, and it couldn't show up. Yeah. I don't know if
which version did I install? Let's see.
I don't know if Sawyer and Melanie has the same problem as me.
Yeah, I had an issue in the beginning, but it's been long I've installed TensorFlow. I somehow fixed it. I think I had the same version problem issue. I've updated my Python, updated my pip, and then I think it worked.
I didn't see my version here. Let me quickly. So you're using 2.7. Is that the latest?
What do you mean? What 2.7? Is a TensorFlow. I tried to install. Hold on, let me check. Install is a 2.3.1. It sounds like for TensorFlow is if it version 2 or higher, has to.
I have 2.1.
2.1.
It's pretty early. I think I updated a long time ago in the summer or beginning the fall. Then I didn't install anything. So that might keep me safe. My Python is 3.7.
Oh, you're 3.7. Mine 3.6. Do you think I better upgrade to 2.0?
Let me see. Let me see if my Python. Oh, my Python is 3.6.4. The same as you.
Yeah, I think so.
I guess you might want to just wipe out Python 3 and reinstall. So
you mean I use a pipe 3 and
uninstall Python 3.
Uninstall, okay.
And
then
redo the same. Install the same version of Python. Don't go too recent. And then do a let's see, install.
I'll try to do this.
Right. After you reinstall Python, install TensorFlow right away to see if you can do it.
Okay.
So semester is almost finished. How have you enjoyed this course? How do you think of this course so far? What do you like? Feel free to share if you would like to talk about it.
I feel like learn a lot of things, but I'm concerning is I couldn't connect this class with the the previously advanced Python class.
Yeah.
Yeah, so
What do
it
you
sounds
mean?
like we learn some basic things and then jump to the very, complex things. And
So you mean the advanced programming is basic and this course is advanced?
yeah,
Okay, right. No, advanced programming doesn't deal with too much of algorithms. The
yeah,
purpose is to be familiar with Python,
mm,
right? And when it comes to machine learning, this course is the beginning point, I think. The real core machine learning algorithms, but you you become familiar with overfitting, cross-validation, um, and those fundamental concepts about machine learning. I think those are the very important uh, aspect. You know, you want to know about it, you want to be comfortable with it, and you want to do
mm,
everything related to machine learning or learn everything with those in mind. You know, so that whenever you train a model, you know you should at least do a train test split. You
mm,
know how to evaluate the split. Um, so that becomes a habit, you
mm,
know, instead of training, fitting the entire data set.
mm,
Right. So yeah, this course does have a lot of topic. Um, you know, take it in slowly.
mm,
When you deal with projects, um, you know, come back to the materials here. You know, it will take some time for you to kind of, you know, have control of everything. So practice every part. In the end, you should be on right track.
mm,
Yeah, great. So this course has a lot, but I intentionally kept it simple. You know, in many areas, it's it's not easy though, right? It's not easy when it comes to um, coding the loop for logistic regression model, for a neural network model. It gets very complex. You
mm,
mess up with one step, you don't
mm,
get the result. Um, I have the demo materials, I have the videos, all, you know, trying to make sure you will catch some mistake if you do have one. But even
mm,
with those, um, so your impression is that it's still a lot of work, and it's
yeah,
still deep work that may cost you 20 hours if you mess up with something, right? I
mm,
think I think that's the nature of uh, programming, especially dealing with models. You know, when
mm,
you have models and programming, then it's easy to mess up. Yeah.
mm.
But yeah, I feel good. After you have taken this course, you are ready to do projects. I assure you. So you can face the real world. Um,
Yeah, because for the advanced the programming class, and I think the final project is do the prediction for the property price, right?
mhm.
And time we're gonna also do the
Right.
prediction on the yeah.
Right. So uh, for let's say, so for that kind of a problem, models, simple models and complex models, they are not very different in terms of the results, because simple models are good at doing those. When you have
Mm,
the variables that are highly structured,
mm,
right, and you clean them well, you do a good
mm,
job in cleaning preparations and understanding these variables, then the result will not be too off. If you
mm,
compare, if you use the most advanced models, even that data size with that number of columns, you won't notice much difference between neural network and a regression model. But so and that's about it. So most teams will do well. Also, in that course, in that project, you don't have to think about different kinds of errors. The only thing you care about is the accuracy. But in real life, that's not the case. You know, you need to analyze the decisions and two kinds of errors, and deal with the unbalanced data set, unbalanced categories. So when it comes to real life projects, people compare ROC curve, people compare the AUC value, compare the F1 value, false negative, false positive. That's the real thing. That's realistic. So in your final project in this course, the data set might be simpler even. It's larger, but it's narrower. It doesn't have that many, different kinds of columns. So that this course is not about data cleaning. It's not about data wrangling. It has to do some part of those part, but I try to simplify it. But the key is to analyze the problem and to, to understand the limit of the model, and also, try to improve the model performance even by 1%, right? See if you can find a way to train maybe a deeper model. Maybe a deeper model will show up some good results here. How to work with the packages, right? To be familiar with the package, because from now on you will be using packages mostly, and packages provide convenience, but packages have some level of opaqueness. You don't have full control about what's going on inside. You have to work with the interface, comply with the way that the package is programmed, and use whatever the tools they provide to get the results. It's not the same as when you code the process. When you code the process, you can get the cost very easily. It's a variable, you just get it. But when you use a package, you have to find the method to get the evaluation metric. What's the method? Every package is different. So that's part of your future work. Okay. Hopefully this is enjoyable. Okay. All the classes here. So this is semester is almost over, and thanks for being part of this class from beginning to end. I enjoyed this course. It's as if I enjoy talking to myself, but I hope that, those words, those comments didn't go wasted, and I hope that you learned something interesting here, as well as challenging. Challenge is what makes things interesting a lot of times. Using open source packages to train an algorithm and to deal with a problem in data science will be the main part of your job if you work in this area. Besides the data cleaning part, so the two parts are interdependent, but what the tasks involved in each part is quite different. The things that we deal with here is mostly about the learning part, machines learning from the data. We emphasize this in this course. All the tasks, homeworks, exams, projects are designed to deal with these aspects, we don't do a lot of cleaning, although text cleaning is a unique case. So this is the last class before Thanksgiving. After Thanksgiving, we also have a Slack class. It's currently TBD. I don't have anything planned specially, but there's a need that is surfacing. Melanie is very interested in learning a little bit more about scraping data. I talked about scraping data, but I didn't demo it. So I think, and depending on what your specific objective is, do you have a specific target website in mind that you are looking to script that website, or do you just want to do some exercises so that you are familiar with what the package is involved? Either way, I can do a demo. It's better if you have a target website, so that I didn't mean to scrape target website, target.com, but you have a target website to scrape. Twitter, Facebook, they have API. It's easier. Maybe Twitter is easier, but other websites, like if you want to scrape CNN, then you would have to use the packages. So I think that class may be used for that purpose. Or if it's not a broad interest, then we can do individual meetings. If you have ideas, let me know. So tentatively, we'll release that class so that you can use it for your own purpose. You'll prepare for final exams. I think you'll have quite a few final exams coming up. So December 2nd, the class on December 2nd can be, self-study time. Great. So let's begin. I have a few things planned today. Mostly LDA analysis, but I'll do a few demos. Some of these demos are also part of the videos I make for homework assistance. In a way, the homework assistance videos become part of learning. So I know that from beginning, I said homework assistants are supposed to be only used for homework when you have trouble. If you don't have trouble, if you can do it independently, that's a better scenario. Yes, but over time, it seemed like class time is not enough. So I gradually include more discussions, explanations, and demos into the videos, but I didn't change the name of those videos. So I guess, for the sake of learning, if you're interested, if you feel some part of that is loose, definitely go back to those videos and revisit those for as many times as you want. All of those are on YouTube. A convenient way to get to those is either by using a link, which is the playlist for this course. You have all the videos. I think over 30 videos or 25 videos are there, besides the class recordings. But another way is to subscribe to my YouTube channel, and you can see everything from there. So I encourage you to visit back those those homework assistance videos. So again, the focus is on text analysis, is the unstructured data, most specifically about LDA, right? Latent Dirichlet model and bag of words foundation model behind it. Let me share my screen. Hold on. Can you see the slideshow? Do you see a slideshow or do you see just a slides window?
Slideshow.
Slideshow?
Yes, slideshow agenda.
Okay. And I'm flipping pages. Do you see the page flipped?
Yes.
Great. Okay. Right. So LDA, but before that, let me talk about the final. The time for the final is December 9th, Wednesday night, 2.5 hours as usual. It shouldn't be a conflict between other finals because this is allocated class time. I will post a review to talk about the coverage of the final exam and how to prepare for it. If you do have a conflict, let me know. There shouldn't be, but just in case. Great, sounds good. So topic modeling. Let me talk a little about the motivation. So what's the purpose of this model? And there's something interesting. There's a silver lining here. If you didn't know, I'll get to it, about the milestone work of this model back in early 2000s, the author of this paper, but I'll talk about that. So in dealing with texts, computers are not very good, just because. Not only because they are A, B, C, D, ABCDs in computers are coded by some kind of symbols, I don't know. I'm making things up. They are coded by ASCII code and some other codes. So inherently they are numbers, but there are so many of them. There are so many varieties. Each word is made up of a few letters, some of them repeated. What did I write? So when you consider the different possibilities, it quickly explode. The dimension explodes. So it's much harder to model for computers. What is a model? A model is a mathematical way to represent the empirical data, right? So a model cannot have many parentheses. Other than neural network model has a lot of parentheses, have a lot of arguments, but it's all structured in a very nice way. And those are hidden structures. Those are not even parameters from the data. Parameters that are dealing with data are not so much. It's okay. All those parameters are created inside the model by itself, based on some kind of well thought design. So that's fine. But if the data requires a long list of parameters to model, it becomes daunting for the computers to complete. So it's hard by nature. So we don't have many good tools. We're beginning to have more tools like these, but still, models available to deal with unstructured data, especially the text data, is far fewer than models available to deal with purely numbers. And it has a much shorter history in terms of algorithms, in terms of text mining models as compared to data mining models. So it's it's a challenging area, but it's also you know, exciting new frontier for machine learning. So the problems are harder to deal with, like this one. If you have a giant library of documents and there's no title and abstract, you do see all the contents, but each article is long, 10 pages or so. Let's say it varies, but putting together a library of 500 million, even if it's all digitized in the database, if you say, I want to read about Python and find me relevant articles about Python that I can learn from to understand what is it, and what's the value of Python, and potentially how do I use it to solve my problem. How would you organize these documents? How would you extract these documents to return relevant results for given some search query? What are the things that jump into our mind? Let's have a little discussion here. So just think wildly. If you know library science, you're in a bit of an advantage here, but I'm not from library science background, so I know nothing about that. I only know what you know when it comes to search for documents, search in Google, search in library system, and databases. That's all I know. So what's your ideas? No ideas? Come on. Maybe the easiest way is to just count the number of times Python is mentioned in each of the document and return those documents that mention Python at least once. This may be the dumbest idea, but it still works. Yeah, any ideas?
Would you use text mining? Text mining?
Text mining? How?
I don't know.
Matching words is part of the text mining, but it's model-free approach, which means doesn't involve any model building.
Okay.
Right. So counting word or matching words doesn't involve any models. It's simply matching, basically. Computers can do that. So will it be good, or what kind of issues will it be involved? If it's just for one search term, the difference might not be huge. So whichever document that mentions Python the most times, the highest number of times, that document has got to be the document that is highly relevant. What do you think? Is a document that has the highest number of mentioning of Python most likely be the document that is most relevant to this term. What might be the other possibilities, or what might be a counter argument here?
The amount of words doesn't necessarily validate the quality of information, you know?
Yeah. When it comes to quality information, that's a higher level of criteria, right? In terms of the content quality, that's something more abstract. It's not only what words are used, but it's about other things, about the writing, the credibility of the information, and such and such. So those
What
are outside the scope somehow.
what
Uh,
I would do
yeah.
is what I would do is since Python is a programming language, I would only look for the documents that are related to computer science or programming languages.
Mm-hmm. So I see. Are you trying to say that by using some kind of reference dictionary,
Yeah.
you can somehow reduce, I mean, a document has, some paragraphs. Each paragraph has certain sentences, right? And each sentence has words. Although certain words will repeat for X number of times, a document may contain up to 300 unique words still. So these 300 words are not that unique from each other. There will be synonyms, there will be antonyms, their meanings are grouped together. So the meaning of the document can benefit from some kind of word, linking by using some dictionaries to reduce that dimension. Is that what you referring to?
Yeah. Sorry, Professor. Maybe I got the question wrong. Can you repeat the question?
No, this is the question.
Okay. So yeah, we're basically looking for the documents with the word Python in it.
Or this is my search query. I would
Oh,
like to learn Python and would like to read about it and know the value of Python and how to use it to solve my problems. So, given these number
yeah.
of documents, they don't have title or abstract. So basically, there is nothing abstract. There's no abstract information about any of these documents that you can rely on. The only thing you can leverage is the content of the documents,
Yeah.
right?
Right, Professor. Yeah.
So
Yeah.
how
Yeah.
do you deal with that?
Yeah. Simple. I don't know. Technically, what I would do is use a back-of-words model with the help of term frequencies.
Yeah,
Uh, uh, I can use term frequencies and LDA analysis to categorize documents,
yeah,
and then maybe that fastens my search. I can find.
right. Yeah, the LDA model is something I'm trying to get at. So we'll definitely talk about that. So you mentioned backward, right? So the idea of backward is basically counting word,
Words, yes.
right? So in a backward model, we have this fundamental component. This is the foundation of the entire model. We have this matrix or table. I will refer to matrix or table interchangeably. in the materials, in the homework, in the video. When I say table, I refer to a matrix. When I say matrix, it's a table. It might be a pandas data frame, but it's more likely in this context, in the LDA model context, it's most likely a NumPy array, two-dimensional. So it's like a table. In this table, you have documents as the rows. So you will have as many rows as your data set, right? Document, what's a document? A document is each of the text value in the data set. A text value is a value of a variable, the text variable for a specific example in the data set. So D would be the same as the sample size or the number of training examples. On the columns, you have T. T refers to term, or word is something that is, that you can interpret. A term is a word. We use 1 gram. In the case of 2 gram, the term will be a phrase. But I talk about all of these concepts, assuming that we're using with 1 gram tokenizer. T refers to the term or feature. So you will have as many columns as there are features that you will like to model. And these features are does not include those weird symbol strings that we learned how to clean up. It doesn't have those terms that are prepared and stripped away, such as stop words, such as words that are extremely short or long length, as well as terms that you exclude. So it doesn't include those. And even with that, you can easily have more than 10,000 features. So more than 10,000 columns. That's a large number. So this is what's called a TF table, term frequency table, or raw term frequency table. Another name is the feature vectors. Feature vector. A feature is a word, is a term. So a column is a feature. A column models a feature. Feature vectors matrix. So same thing. What does each cell or each element of this table model? It's an integer between 0 and as many words as they are in the document. And this value represents the number of times that the feature, the term, the word, all these things refer to the same thing. The number of times that the feature can be counted or appears in this document, assuming that this feature is what's retained as one of the features. So this is what the bag of word models is based on. This is a term frequency table or matrix. And based on this, you can do a lot of things, including the LDA model. So now, why do I talk about these? In solving the problem that was raised in the previous slides, one dumb way is to count number of times Python is mentioned in the document, and you rank the number of times that Python is mentioned in all the documents, and those documents that mention Python the most times might be the ones that you're looking for, right? So this is essentially based on the backward model. If a feature is Python, this is the term. But in this table in this matrix, it cannot use Python literally. It has to assign an index value, say 100. So this index value 100 is assigned to Python. It's a unique identifier for this term in this model. So whenever you want to refer to this feature, you use the index value 100. Python is the term that's in the back of it. So this feature is mentioned. Let's see. Let's say in this document, 50, it's mentioned 10 times. In this document with row index 100, it's mentioned 20 times. It's not mentioned in any of the other documents. So maybe these two documents are what you're looking for, right? Fair? Simple? Reasonable? Yeah. Up to this point, it is. But let me remind you that articles have different length, right? If I tell you, well, if these are the only two documents that ever mention Python, I guess this library is old. So if there are only two documents that mention Python, then these are the only thing that you can read about Python anyway. So you would extract them. But if I were to ask you, let's say this is document 1, this is document 2, by merely knowing that the number of times that each of the document mentions Python, can you rank the relevance of document 1 versus 2 solely based on this information from the bag of word model, from the term frequency table? Can you do that? Why or why not? What might be missing? Based on the raw count, document 1 mentions Python 10 times, document 2 mentions Python 20 times. Would you jump to the conclusion that document 2 is more relevant?
No.
Why not?
Maybe document 2 is a research article which is talking about Python, inception of Python, how it really came into existence. You never know.
So Python is just a tool, or I guess is one of the topic that is mentioned in article 2.
Yes, sir.
Right. And you mentioned that it's academic paper.
Yeah, possibly, sir. Yeah. Yeah, because our goal is to learn Python and not know about Python. So
Okay, right. So this says something about terms do not necessarily represent the purpose of the article, even if it's mentioned a lot of times.
So,
yeah.
one more point is that Python can be a snake too. So if it's a programming language or it's a document on the reptile, what is a snake or something, we don't know.
Okay, that's interesting. Yes, definitely. Right. So it's about animal science, reptile. That's interesting. Great. So, just by knowing the word count or frequencies of mentioning, you don't have the whole story. And also another thing that kind of is mentioned by Soria, but not entirely, is that what if I tell you that document 2 is basically a book which has 10,000 words, but document 1 is a short article with only 300 words. So now you see which now you see the importance of Python in each of these documents. Python is definitely more important in the first document than in the second document, just because of the relevant weight, right? And this information, length of the article, is missing from the term frequency table. It does not. It ignores that aspect of about the document. That makes sense? And something that Sahir said about, Python can be interpreted as in two contexts: computer science versus animal science. And this is the context. So I got disconnected. Can you hear me?
Yes.
Okay, great. Somehow. I don't know how much did you miss? I was writing the context, but I guess you didn't miss too much. So hold on. So the context is also not captured by simply the word count, right? So there are many shortcomings of simply counting the word occurrences, even though this could be helpful in some cases, but not universally. It depends. So that's the point I'm trying to get at. The problem with dealing with modeling text data is because of the high dimensionality. There are so many unique words, even in one piece of article, and not to mention when you have a large corpus, the number of unique words explode. In information retrieval, the basic tool is the TF-IDF. It includes two concepts. The one of them is the concept that we discussed, the term frequency. It does have some utility, but it has shortcomings. When it comes to importance of the terms, weight of the term in that document, this have a great influence on if that term is important to the document, even if it appears the most frequently across in that document as compared to all the documents. And relevance is related to the context about, a single word might have different meanings, and it could mean very different things just because of the convention that we use that word. So this part is also missing from term frequency. So what can you do, right? Something that will come handy is the document frequency. And document frequency helps complete what needs to be considered in this big picture. And this is a great idea, great invention. Term frequency is a great invention by itself. Document frequency is a very convenient, easy, low computation method to add on to topic frequency that complements the capability of term frequency by completing the other two aspects. The term frequency, when it comes to definition, what does it mean? It counts the number of unique documents that each term appears. So how many times is this term mentioned? Hold on. No, not how many times it's mentioned, but how many documents contain this word, regardless of how many times it was repeated in those documents. It counts the broadness of the term when it comes to the corpus. What's a percentage of the corpus that includes this word for at least once? This term frequency captures or represents how less important the words are based on the term frequency, based on the document frequency. So the
I have a
larger,
question real
yeah,
quick. Sorry. So choose somebody mentioned, Python could be a snake, which is kind of what I was thinking too.
right.
So how could you do a search by 2 words? So like do Python and make sure that, a computer or program or something is also in the search to make sure that it's relevant and it's not just talking about snakes?
Oh yeah, definitely. Um, adding one more term um, does seem to be the most reasonable fix to that issue, right? Computationally, though, it does add a lot of burden to whatever the search engine, because here there are 2 terms. Do you count the total occurrences of the 2 terms? Do you restrict those? Do you restrict the search to only those documents that has to mention both? What if it found a document that only mentioned Python? Does it return the result? Does it consider the result? Right. So a lot of nuances to think about. But again, the purpose of that example is not exactly to talk about context. Believe me, context is one of the, is one of the hardest problem that Google is still trying to solve. So it's a research in progress still. When it comes to language, when it comes to computers trying to understand what we mean by these languages, we are far from, solving all the problems. But, Google obviously solved the part of a search engine by using bundles of terms, right? So if you're interested, you can refer to how Google solved this problem. Search engine has a long history, I think, ever since computer is born, even before Windows is born. I think this is part of the library science. So, when computers are born, libraries have these equipments. They can search for books, and the database has abstract information about those books and resources. It doesn't have the full text, but it does have the abstracts and subjects. So search engines will be helpful in library science. Yeah. If you're interested, take a look at those literatures. Here, what I'm trying to say is document frequency helps solve some of those problems, even without having to think too much about how to model context or adding the complexity of, term bundles. So how does it do that? Term frequency measures how less important the words are. So in other words, if a word appears in more documents, it becomes less important. Not in the sense of the not in the sense of the meaning of the word. Obviously, if it's mentioned a lot, it's got to be important topic. Otherwise, you know, why do we have more information for those? Amount of information kind of is governed by how important that is or how useful that information is. This doesn't mean that this is discussing in the context of document discovery, text discovery, discovering those documents that are most relevant and unique resources out of a bunch of them. So then how does why does it mean less important? If a word is used in every document, what does that mean? It could mean two things or two scenarios. If a word is used in every document, it might be a stop word. For the sake of, because of a linguistic conventions, we use stop words. We have to use these because they help us understand meaning, to complete the sentence, to convey the meanings. So this is part of the writing style. But any basic passage would have to include these stop words. So stop words obviously doesn't help with text mining, right? You would, or in other words, you would definitely not go into search resources to learn what is the word to. You are not going to search about it. So, so this word wouldn't be important in terms of information retrieval. We're talking about retrieving important information. So, but the words that appear in almost every document are not limited to stop words like to. It might be because of another scenario is when the library, the corpus, is about a domain, a large domain, but it has different subdomains. So the context here is about a specific domain, although it's large domain, but it's all about a specific domain. Let's assume that the domain is politics or US politics. So that's the domain. Every piece of article is talking about something about US politics. So you would be sure to find politics, this word, to appear for many, many times in terms of the number of documents that have this word. So in this context, US documents, if you are searching for information in the US politics, a word politic, the word politics is almost certainly not useful to you because, it's already known. It's also already assumed by the purpose of this person who's going to retrieve information. So to generalize this concept, a word that is mentioned by overly many documents in a corpus becomes less useful in terms of finding the relevant documents for you. Otherwise, you'll find too many documents. The search becomes sort of infeasible. That makes sense? So by somehow incorporating document frequency, is the frequency of words being mentioned in documents, incorporate this document frequency, the concept, into term frequency, you can limit the focus to those terms that are unique enough by using a threshold value to remove those both the words that are used too often, not necessarily stop words, but there are other words that are used quite often, and as well as those words that are meaningless in the context of the current corpus. So both situations, document frequency can help you limit that. So that's why TF-IDF becomes a sort of a cornerstone of many of the text mining models. You can even use the metrics that are results of term frequency or TF-IDF, you can convert a document into, let's see, you can convert a corpus into, hundreds of columns, which are the features, right? And these features are weighted by the TF-IDF metric to somehow denote the value, informativeness, and uniqueness of each of the feature in this corpus to a particular document. That also considers the number of times that's repeated in the current document. So you can use these the metric the matrix with these columns of the features to train models to train supervised learning models to predict an outcome, such as sentiment analysis for Twitter messages. It's a standard way to, it's a basic way to construct variables for the tweets to predict the sentiment. It's a well-known standard approach to do sentiment analysis based on only the text. By only using the text, you can train a model that achieves an accuracy of close to 90 or over percentage of accuracy, even though the data is not balanced. It is not unbalanced; it's quite balanced. Twitter messages, close to half is positive, close to half is negative. With that, you can achieve a good accuracy level by using these features. So they are quite important, quite useful in terms of text mining. Okay, and based on these concepts and the limitations of those that we discussed, TF-IDF doesn't solve all the problems that we need to solve. For instance, if you have that large library, how do you categorize different documents? TF-IDF may be helpful for you to search for document based on keywords and rank them in terms of uniqueness and relevance, and may do an okay job, but it doesn't help too much if you were to categorize the large library into different sections. This is sort of like the categories or domains of knowledge. TF-IDF doesn't help you because it's not a model. It's not a model based on parameters. It's a description of the text. So there needs to be a model. Latent Dirichlet allocation is one of such models that is very popular now. It's being used in text mining and text discovery, text categorization, even computer visions, but there's some weird with deep learning. This method kind of becomes obsolete, but it was useful in the part of that literature. And latent Dirichlet model, if you notice, the second author of this article is the very famous Stanford professor who used to be a Google engineer, a Google programmer. This person, Andrew, last name N. So if you didn't know this is kind of a happy, good surprise that, Andrew N, the reason he's very famous now is because he knows the stuff, and he is a pioneer of the machine learning field. And if you were to read this article is very good. From an academic point of view, when I read the article, it's clean, it's clear, clean, and explain things very well, using language that you can understand. And the model itself is quite comprehensive. I'll talk a little more about that model, but this is, something that you should know. Or if you don't know this person by name, then maybe sooner or later you will know that. I think if you continue to deal with machine learning, you will know that. Okay, so this model is based on the LSI, and there's other variations of that model. In the literature, the models, they are not very different actually. LDA, LSI, based on term frequency, but builds upon a probability model. But LDA adds unique features to the model, so it's a significant, I guess, improvement in solving new problems. Any questions here? I think we'll take a little bit more time this time, considering that this is the last class before Thanksgiving. So it's kind of we're going to celebrate by spending more time here to kind of worship the topic. I'm kidding. I'm not going to go too much overtime. Any questions here? No? Good. So I have a few more words about this term frequency, because there are some questions in the homework that deal with this. I draw this. I use DF2 as the example. In the demo, I'm using DF2, so that's why I carry the same picture. Term frequency table matrix. It has a number of rows that's the same as the document, as the data set size of the data set, and number of columns as being the same as the number of features that you allow for the bag of words model. I'll show that in the demo. Notation is that, but it didn't really say anything. The purpose, the meaning is quite important. So the term frequency counts the number of times a feature appears in a specific document. So this is the raw count of the number of occurrences. The rows represent the examples. The rows is equal, the row index is equal to the row index of that specific text value. The column index refers to the index value of the unique features as used in the vocabulary of the bag of word model. A bag of word model basically turns tens of thousands of words. This is a review. Some reviews are longer, some reviews are shorter. It basically turns a corpus into this matrix, and that's it. That's the only thing that's retained after converting that text. So it's a simplification of the original data. So this is one column, that's another column. Skip that. The advantage is that it reduces the dimensionality of the original text data. That's huge. It makes it so manageable that any computer can handle it. For the text data, to put it into a structure, it's kind of daunting. So it simplifies the problem, still retains useful information in the matrix, makes it possible to build models using these features. the raw counts, it doesn't get very complex. A lot of these values will be 0 though, because not every word appear in every document. And there are a large number of words that appear only a few times across the documents. So those are in the tail. The distribution will be highly skewed when it comes to commonality of the words. A large number of words are very uncommon, and they appear only for a few times. Let's see. So by this representation, there's a critical consumption of a bag of words model. This way of representing the text means that these words, take this word and this word, these two words, they are just two columns, but in the text, they may have to appear, one may have to appear before the other. There's a logical order when it comes to using these two words in sentences, right? When you say, this is just an example, but when you have to use have to mean that you should do something, have to, you need to put have before to. You can't do the other way around. But the bag of words model does not account for that. This part of the linguistic rule is completely dropped. So the critical assumption of bag of words, or the essential meaning of bag of words model for the text, is that the order of the terms don't matter anymore. They are the order of the words information is completely dropped, lost in the bag of words model. The bag of words model does not consider the order of the words entirely, or not at all. It doesn't consider the order of words, not at all. The only thing that matters is what are the words that appear in this document and for how many times. That's it. So, and other than these weaknesses, when it comes to modeling the text data, bag of words model makes that critical assumption. So keep that in mind. Here is some illustrations. In the normal text, we say Python is superbly interested. This is expressing some, amazing feelings about the Python. But what if there's another way to use these 4 words to express different feelings? If somebody's name is superbly, it could be possible. He's saying, is Python interesting? This is casting a doubt on Python, a very different feeling from the first one. But these are 4 same words. Assuming we were to retain the is, eventually we will drop. We may be dropping because this word is a stop word, maybe, but doesn't affect too much. So a bag of word model will represent both data as a list of 4 features, a list of 4 features. So in bag of words model, the 2 data point is exactly the same. So you do see that the feelings are lost from this way of coding and modeling the data, right? Term order does not matter. But still, it gets the job done. The term frequency table retains the basic information about the words and the features used. The basic meaning of those articles are preserved by means of those key terms, but it also reduces the dimensionality so that you can quickly model by using the features. You can predict straightforward target variables about the texts. So keep this in mind. This is very important. Questions? No question? Good. So that's term frequency. I mentioned document frequency, and here is an example of representing document frequency. So basically, if you have a term frequency, you know, this is document, this is T, and you do the column sum. You take the sum of the first column, it becomes, but when you do the sum, you do not sum the whole values of these. You sum the unique documents that has values bigger, larger than 1. So it's a unique sum of the unique. So you take the unique sum of unique of all the columns, and it in the end you get even a column. You get a column, and this can be thought of as the index of terms. So for each of the term, how many unique documents contain this term? You may have a lot of the terms that only appear in a few of in a small number of unique documents, but you have still a large number of terms that appear a lot. These would be the common words. But for words that appear in over half of the documents, this term may not be as useful. It will return so many results that you can't keep track of. It is those words that only appear in a few documents that indicate that these 3 documents may be talking about a subdomain that is relevant if, you know, if the purpose of the search is indeed related to that subdomain. So document frequency adds in this sort of the broad, the context of the aspect of the word that relates to the broadness of that subdomain. And we don't use raw TF. In fact, we use IDF. This is the formula. We will not deal with this directly here. Okay, so comes the interesting part. So we'll work with this Yelp data after cleaning. If you downloaded the new updated demo Jupyter Notebook, all the codes are included. You can run them all the way until you get the data frame 2, DF2. So that would be the data after cleaning the symbol strings and also preparing and pre-processing, including the tokenizing and lemmatizing. So the demo will start from there. I've already run those codes. So before we begin, just for fun, there's a question. So of the entire corpus, you'll think of the 15,000 review texts. And what's the average word count what's the average length, which is a character count of a typical review content that we analyzed last time? Do you remember? I thought it was 80, but it turns out to be way more than that. I thought there are only 80 characters in an average Yelp restaurant review, but it's more than that. Do you remember how long is a typical review? Yeah, I don't remember either, but it's way more than 80, maybe several hundreds. So of all the text reviews, after removing the symbol strings and the stop words, So those words are gone. Like a, and, the, to, these words are gone. What are, can you guess the three terms, three words that that are mentioned most frequently? This is across all the reviews. Definitely the three most popular words in Yelp reviews of restaurants. Can you
Would
guess?
one be terrible?
Huh?
Terrible?
Terrible. Terrible.
Yeah, because people usually leave reviews for when they're mad.
Right, right. Yeah, I'm with you. When the food is mad, and when they write about it, terrible, yucky. No, I don't know. Terrible. Yeah. If the food is not good, or if the service is not good, doesn't matter. Yeah, anything is not good, they will complain. But you know that on Yelp, the majority of the reviews are favorable. So close to 75% of the reviews are above. Close, is it 75? Let's see, at least 70%. Close to, or
Well,
at
then
least 70% of the reviews are 4 stars and above.
maybe I just always have bad experiences.
So you're one of those few unlucky. Now, the thing is, when people have mediocre experience, they don't complain, and they don't say good either. So they don't submit a review, because no, why bother? It's only when the service or the food is so terrible. I mean, I guess this is. I don't. I won't even try drawing, because it will turn out ugly. Um, I'm thinking about a thumb down. A thumb down. When the service or food is really terrible, people will think they are betrayed, and they will, try to sabotage. And that's when they, will submit a bad review on Amazon or Yelp. Um, but for most of the businesses, this kind of treatment is fairly rare. So most people have a fairly good experience, and people would like to spend time on social media, and that's just the nature of users' behaviors. So when the majority of service is okay or good, and when people would like to spend time on social media, they say good things about um, their experiences, to in a way to promote themselves, right? Otherwise, why contribute a free review without getting anything back? The social media reputation is what they get back in how they can be favorably seen by their circles by writing something good about something that may be really good, right? So terrible is a proposal here. Um, Korean said something has something to do with the stuff that you go to, that you go to a restaurant for. So what
Is it
might
food?
that be? Hmm?
Food?
Food? Who said that?
Sahitya?
Uh-huh. Food, a good one. We'll see, but definitely sounds very close. A word that describes the stuff. Terrible is one guess. Something else?
Delicious.
Delicious. It's a long word though. Let me
It is.
try to. Let me DIEALICIOUS. Is that right? Hopefully. Yeah.
Yes,
Delicious.
yes.
Yeah, yeah. Terrible, delicious, you know, two poles. So if you think of anything, just speak out.
Good.
The third, good, good food, good food. Is that how you write your review? um, yeah,
Great
I mean,
place.
simple words. Yeah, simple words is what people use most. Clean,
No, great place.
great place. The third one, are you talking about the third one?
Uh, yeah.
Yeah, yeah. Okay, I'm starting. I'm starting to have a feeling that you have already um, analyzed the data, because these are getting closer and closer to the final answer. But this is quite fun. When you look at the most popular words, you'll realize that um, when it comes to reviews, it's um, let's see, people use simple words in most cases. Simple words that gets the job done, easy to understand, and appear to be, you know, based on the words that people use, you kind of have an impression of the people who use those words, right? Uh, People are just being people. Um, so, right. So three simple words. We'll look at that in the demo. I think so. Let's look at demo, and I'll talk a little about the term frequency table and what that means. So let me change the share. Wait, hold on. Oh, here. Okay. Do you see the Jupyter notebook? Yeah. Okay, good enough. So for LDA, for this part, feature vectors matrix or term frequency table, you will you start. So we're using scikit-learn. You start with a model inference, a model instance of the vectorizer. This model, this transformer will transform a document, which is the review text column. We'll transform that column into, we'll first construct a dictionary or a vocabulary, which is a dictionary. And based on that dictionary, it will transform this data set into the term frequency table, the two-way table. So the term frequency table is the result, obviously. It's a sparse matrix. So when you slice it, it won't return the exact values. It will give you a pointer because this is sparse matrix. You use the two array method to extract the actual values of those places. These are all zero because this document simply doesn't have these terms, but we'll look at those relevant numbers. So I will use the first example. In the first row of data in the review text, after being cleaned, this is the review. You can kind of read, but it's hard to read with all these tags. Plano is the city of Texas, I guess. Company, conference, this guy went to a conference, and there's an event that happened in somewhere at some time and with his colleagues. Oh, it's really hard to read. For sure, this is for a restaurant. Okay, so I'll use the first term here. This term has a unique index value. And what is it? We can use the vocabulary component of the transformer, the vectorizer, this component is a dictionary. It takes a term, a key. A dictionary is key value pair. It takes the key, which is the term, and return the value. And the value here is the unique index value for that particular term. So that means this term is modeled on the column with index number, with this number as the index number. So by using this number, term index, and by using the row index, which is the first example, you can extract the content, the value of the term frequency table, and it's 1. What does that mean? Term frequency table models the number of times that a term appears in a document. So 1 means that term only appeared once. So let's search. Let's search by using the browser. So, in this long text, this term only happened once. So this is correct. So this shows how to get the index value based on the term, and based on the index value, how to get the term frequency, the raw count. You can also do one another thing. You can use the index value of a term to get the term itself. Because when you look at the term frequency table, you can identify those terms that appear the most frequent in a particular document. But the only thing you get is a column index. This column index doesn't help in terms of interpret the term. So if there's a way to get the term by using the index value, that would be great. So this is how you would do that. Here it explains what, how to interpret the term frequency. It should be helpful in the homework. So what I will do is I will use a term index, the column index for the happened, I think that's happened word, and print a few more rows as its neighbors. So I slice several columns. I slice 4 columns of that first row. And let's take a look at the term frequency values. So I get 4 results. This one is actually the term index. By using the term index is not 1, but by using the term index value, I get 4 results. The third one is the same one that I got earlier, because I started from 2 to the left of the term index. So I have 2 more results before it. I end right before 2 to the right. So 2 to the right, the second to the right is not sliced. It's sliced right before that. So there's only 1 more after that. So this one is the same one. And the next column doesn't have, the term didn't appear in this document, the same with the one, 2 to the left. But the term 1 to the left appeared also once in this document. So I will use that. And you know that this term should have an index value of 1 of term index minus 1, because that's 1 to the left. So this is how I get that. To get the term by using the index value, you need to do 3 things. You need to get a feature names. I made a video to explain this, so you can look at that in the homework assistance video. Feature names is a convenient way to get the term by using the index instead of get the index using the term. So, you know, flip around. You can use this feature, you can use this method to get the list. It's a list. And by using an index value for the term, you can get the term itself. And the term index is the one less than the earlier index value. So this one is happen. So it's a variant of happened. It's interesting that happen and happened are close to each other, maybe because it's alphabetically sorted. So happen and happened are very close to each other. They have very similar index values. Happen is a word. So now you can go back and forth, right? When you have happen, you can get the index value, and that index value should be one less than this large number, 1,900 something. So we can do that by using the same function here, count vectorizer the vocabulary and give the term. So we can quickly do that. So 1974, which is one less than 1975. Yeah, you confirm. You can go back and forth by using this, you know, these codes. All right. So let's do this fun task. Let's get for the first review. This is only for the first review. So use the row index. Use the row index. Use the row index here. Where is it? Use the row index here. Can you get the top 3 terms of the first review text? And how do you do that? By using the term frequency table. How will you do that? So you basically, it's an array. It's a one-dimensional array. You want to get the terms. You need to first identify the largest numbers, the 3 numbers that are largest in this array, which indicates that these terms occur most frequently in this document. Then you need to get the index value of these 3 values, because by using those index values, you can get the terms. You cannot get the terms only by knowing how frequently they appear, right? So index value is a link between occurrences and the terms. So the method that you will use to sort the value and get the index in one step is the arg sort. The arg sort. It will give you the sort, and then use a special slicing notation to get the last 3 and then somehow flip them around to rank them in descending order of occurrences. So then by the end, you will get 3 indexes referring to 3 frequently occurring words in the descending order. By that, then you can get the 3 words by using the feature names lists, and here it requires a list comprehension notation. So quite interesting task. See if you want to challenge yourself to get that. I'm going to do this. So I'm going to review this answer. What are the top 3 terms of the entire corpus? The first thing I need to do is, you know, regardless of the document, I need to, hold on. Okay, when I did these, I I didn't calculate the document frequency. Document frequency is about the unique documents that contain the term. When I calculate these, I calculate the raw count. So I calculated and obtained the 3 terms that are repeated the most number of terms, even counting the repetitions in the same documents. So this is definitely a raw count of the frequency of the terms. So by using the term frequency table, I need to sum over all the columns to aggregate over all the documents, right? So I need to get the column sum of the term frequency. So I need to do a sum operation here, and I need to specify the axis. Maybe the default axis is summing all over the row or the columns, but I just want to make sure that I do it right. So by the end, I should have, but there's something tricky here you want to remember. When you are dealing with a term frequency table, remember that this is a sparse matrix. So when you do these operations, it will give you weird structure for the result. So to be safe, always return an array and do the calculation. So by the end, I should get a one-dimensional array. I get 5,000 because I have 5,000 features. So these 5,000 values represent the number of times that each of these terms are found in the review text by counting the total number of occurrences. So now I need to get, this is similar to, from this point, it's quite similar to here, without specifying the row index, because I'm only dealing one row. There, you're dealing 15,000 rows. You need to specify which row, which is the first row. So I'm going to use the column sum result, and I'll use arg sort method. This will sort the values according to the values. This is the sorting based on the occurrences, based on the frequencies, based on the counts. And after sorting them, it will get the index value, but I only need those index values at the bottom of the list, because the 3 terms that occur the most time is ranked at the bottom. It's ascending order. So I get the index value of the bottom 3 elements and do a reverse. This is the way you do the reverse. The flip, completely flip around the list. And so now I get the term index values of the overall most frequently occurring word. I get 3 index values, and based on these 3 index values, I will get the terms, right? So when I print, this is a list, I will use a list comprehension for I in this term index overall. For element in this small list that includes 3 values, for each of these, I will extract the term. We'll use the feature. Somehow I clicked. I see. This pen is messing with me. For each term, I will need to use the feature names list to extract the term by using this. So by far, it's almost complete. I should get the 3 terms, but these 3 terms include the POS tags. hold on. I don't think this is right. Do you get the same result? Interesting.
I got different results.
Yeah, what are your results?
Food, place, and good.
Food, place, and good. Yeah, exactly. That's what I got earlier. But what did I get wrong here? Frequency axis, and then I do the arc sort, get the last three and turn them around. Feature names for index in this. Oh, I think I know why. So this this term frequency table is the result of the vectorizer. And when I construct the vectorizer, I pass an argument as for document maximum document frequency. Only those terms with document frequency below this point, this argument, this threshold is retained. Otherwise, it's dropped. So when I set this value very low, it's going to get rid of all those popular words because this is a threshold to cut off the popular words. So in order to do this specifically, to do this task specifically, I would need to update that bag of word model by using by setting the max df as 1 to make sure I don't drop anything. And I think the result would be very similar to one that 10 got: food, place, and good. But I'll let you do the experiment. If you get very different terms, let me know. I think my result earlier was based on max term frequency of 0.5. So so still, those very popular words have already been dropped. So I will let you experiment with it. So to finish off here, to get the three terms in the first document, you will refer to, instead of using the column sum, you will use an index notation to index the first row of that data, the TF table, the first row, and then do the arg sort and do the same slicing. You will get three values, still three values. And by using a slice notation, by using list comprehension, you can get the three terms. So that's how you can get that. Okay, great. Any questions? Let me get back to the slides. Okay, so my previous result is, this is food, this is good, and I think this is place. Yeah. Right. I thought it's quite fun. Are you going to use these words when you make a review? Will you mention food? I don't know. I will discuss that when I talk about the latent Dirichlet allocation model. All right, so let me move on to the model. This paper is the milestone paper. This is Andrew, and I think he was in Stanford at that time. I don't know if he's a professor or a student, but it's a hierarchical Bayesian model, if you know what that means. I will not go into that. Bayesian. And they coined the term topic in that paper. Although that paper is not only, it can, they mentioned that, they specifically point that out. It doesn't have to be text corpora. It doesn't have to be text analysis. It can be computer vision, or it can be any a model that deals with any collections with elements in it. But in the context of text analysis, they coined the term topic. So this is quite interesting. You know, you have the term frequency, you have the document and the term. It seems to be complete information about the words that are used in the document. Yes, when it comes to terms, the term frequency table is complete, or somewhat reasonable at least. But when you want to extract meanings or theme, or domain and context, term frequency is not very useful. Meanings, theme, domain are something. Meanings is a little bit about the words, but theme, domain, context, or idea is a very high level abstract word. So quotation here. When it comes to theme, domain, context, it is about an underlying concept. It's an implicit concept of the words. Words are a reflection of the theme. Words are a way to describe the theme, the domain, the knowledge, the context, the idea. But words are not them exactly. You know, you can use different words to basically express the same feeling or similar feeling, but those words will be very different. So by focusing on the words alone, the model cannot get to these abstract and latent concepts. So there needs to be something that is modeled in order to extract this part of the information. So that's the idea behind it. But you know, these authors are not the only one to think of it. They basically come up with a probabilistic model that becomes very useful in the context of text mining, but they are not the inventors of the terms. So topic becomes the glue between the document and words. So if you think about it, you have a bunch of documents. I can use this. You have a bunch of documents, right? And you have many terms. A simple way to model this relationship is to draw links. The first document has these words, right? The second document uses these words. And third and fourth, third document use these words that are unique. Okay, so that's one way to represent the relationship. This is more descriptive. This doesn't involve any model. It's describing the word frequencies. But alternatively, you may have something in the middle that captures what they say topic. Or we can say theme, domain. You know, these are different ways that you can interpret what means by topic. You know, the purpose of using topic is not to restrict the interpretation. It's just a way to communicate, a quick way to communicate the purpose as a model, but you can have different ways of interpretation. So you can say that another way to represent the relationship between the documents and the words is by topics. Given the topic, for instance, given this topic about computer programming, these documents can be related to or identified as related to a computer science document. And because they are computer science documents, it becomes clear that they will almost certainly use some of these words, but not the others, right? Computer science documents may not talk about the United States president very often. So by using this, you kind of see the relationships between the documents and the words in a different perspective. And that's very smart, very intelligent. That makes sense. And that gets you one step closer to what's known as a model, rather than a descriptive representation of the documents and words, right? So it's really a model. So it's trying to describe the back of it, the underlying knowledge, if you will, knowledge of that latent Dirichlet allocation mathematical method is trying to describe a data generating process. This, you know, for anybody who's familiar with statistics, statistics deal with probabilities, although they are non-parametric, but statistics deal with probabilities. And when it comes to modeling the actual observations, observation is empirical data, is the realization of data is a realization of the underlying phenomenon. So when it comes to the probabilities of those realizations, what the statistics are really dealing with is to try to uncover or try to think of and try to use data to recover or prove or examine the data generating process. What that means is that there is a model. They typically use phi. There is a model based on a few parameters is a abstract way of describing a phenomenon based on these parameters, and there is a rule that govern the rule by which these parameters govern the actual realization of the um, phenomenon. We get to observe whatever we observe, but regardless of how the observation changes, the law doesn't change. So this is what they call a data generating process. A simple example will be the um, this dice, rolling a dice. So when you roll a dice, every time you can get a different number, but you can only get one of six numbers. If the dice is fair and square, you'll get 1/6 chance. You'll have a 1/6 chance of getting any number. But if you roll 10 times and I roll 10 times, your sequence of numbers will be different from mine because of chance. But despite all these differences and variations, the law that's governing what you would get and what I would get is exactly the same. It's the law of probability and law of chance. So that's what they mean. So latent Dirichlet model is a probabilistic model. They also call it a generative model that try to describe the relationships between documents and terms. And it's a improvement upon the previous models that also deal with the latent dimension of these concepts. So that's as deep as I want to go with LDA. And let's do the fun stuff. Demos. Let me get back to the demo. Any questions about these slides about LDA models and the conceptual side? Right, great. So one thing that kind of make you a little bit uncomfortable is similar to how a k-nearest neighbor model is to some of the people, is that you have to know how many topics to model. There is no quick way to have a universal rule. There also is no good feedback mechanism for you to know, did you pick a good number? No. So you would have to avoid being crazy. So don't put in 1,000,000 topics. There are not even 1,000,000 documents. How can it be 1,000,000 topics? So, try to be reasonable. And for a reasonable size data set, text data, people usually, based on what I see in academic papers, is between 5 and 50, something like that. Mostly people use 10. When I run LDA in my paper, I use 10 because I deal with the review context, and based on a data set that has thousands of text values, 10 topic seem to be a reasonable number. But I should say that when I use LDA, the kind of results I get does not always come out to be conforming to what I thought that I would get based on LDA. I thought I was getting topics, but what I got doesn't seem to be really topics of the reviews, but seems more closely related to the style of the review, the way they use the words to write their reviews, to express their feelings or thoughts. So in certain contexts, even though it's a well thought it's reasonable to think that LDA will give you the dimension of the topics by returning those top terms in those topics. When you look at those top words, it doesn't seem at all reasonable to you that these are different topics, but it may be really something else, a writing style. It could be. So that's one example in my experience of using that in an empirical setting. So I picked 10 here to demo just because 10 is a number that we can manage. If there are 50 topics, it takes a lot of time to go through the terms and figure out the differences and similarities between the topics. 10 is a reasonable number. It's not too small. If it's too small, you guarantee you get some different results, but if you run them by using different random state, you will get totally different results. So it's hard to keep track of. So 10 is kind of reasonable. 5 is also good. Between 5 and 10, you'll get slightly different topics. But when it comes to food review, you do have this space of possibilities. You know, you'll by the end you'll see what these topics really are. But you can imagine that when it comes to food, these are different types of food. You know, we do have 10 or more than 10 types of food available on the market. So 10 is reasonable. I will not run this now because it takes some time. After training by using 10 topics, but by restricting to the words that have document frequency lower than 10%. So by getting rid of those highly popular words, those words as good, place, great, food, those generic words, those are not very helpful in identifying unique topics. So what's left are quite unique topics. Let's see. So after training the model, I will get the most likely topic. If you're getting the most likely topic, you only need to use argmax to get to get the index value for the probability estimate that is the biggest. But I like to examine the top two, because if I have one probability estimate of close to 50% and the other estimate for the second most likely topic to be close to 40%, the two are not closely distinct from each other. So in that case, the review might not be as good. When I look at, so if I were to extract the two most likely topic here, then I will need to use the arg sort and take the last two of the index and do the flip and get the index. Based on these index, I will get the probabilities from the results that are returned from LDA model. When I train and transform the term frequency table, the result that's returned from the model is the document topic probability distribution table. So I can get the most probable topic for a specific document. The most probable topic is topic number 6. And the second most likely topic is topic number 9. The difference in probabilities are quite large. One is the majority is over 50%. The other is only 22%. So this result is good. You know, the model is quite confident in identifying the most likely topic. And based on this topic index 6, I'm going to get the terms. To get the terms, you need to get the index value of those terms. So you will use another result of the LDA model. It's an attribute of the model after training. It's the components that gives you the topic word distribution table. It's a table that measures the relative importance of the terms. and it's organized by topic and term. There are as many number of rows as there are topics. So there are only 10 topics here. I have 10 rows. Each of the column is similar to how the term frequency table is organized. Each of the columns represent the term, and the values of this matrix represent the relative importance. It's not the raw count, but it somehow incorporates the idea of count, but it also incorporates the relevancy part. So it's the importance of the word to that topic. This is topic word table. I use the same technique, arg sort, using the index value row index. This is the topic index. Sort, get the bottom several 10 words, and flip around and get the index of those terms. By using list comprehension, I get the terms. So look at this. Topic 6 has these top terms: good, cheese, place, chicken, sandwich, salad, bean, barbecue. This is quite obviously a traditional American cuisine. Yeah, agree? Because there are burgers, there are sandwiches, there are salad, no salad, potatoes, beans, and salad, yeah, barbecue. Yeah. So if you want to get rid of the POS tag, you can use a method, the string method here, split and get only the first part. You get rid of those tags. If you have any questions in understanding these codes, feel free to let me know. Finally, to get the top words of each of the topic, we only have 10 topics. So I do a for loop. I also explained this in the video, so go check that out. Basically using the same example. But over there, I only specified 5 topics to make it easier. So based on the top words of these 10 topics, here is the topic that hold on. By using, earlier, I used a higher number as in your version of the demo Jupyter Notebook. I use a larger value for the term frequency, the max term frequency in the bag of words model. So what you got have a lot of repeated occurrences of food, place, good. So if the topics have these common words, the topics become less meaningful. Agreed? Because these words don't represent the unique topic. So in this case, what you need to do is to reduce the max document frequency argument and retrain the bag of words model and retrain the LDA model. By the end, now I'm using 0.1, so the results are very good. Hold on, not good. This is, okay, I didn't run this. This is the old result. So these have a lot of the common words here. We need to get rid of those. So I retrained the model by using lower max DF. By the end, I got these results. They're much better. Topic number 6. Okay, anyway. After retraining, the order of the topic will change. So these are interchangeable as in the original paper. So traditional American cuisine should be close to somewhere here. Number 4, pizza. Staff 1, wait, hold on. Anyway, somewhere here, traditional American cuisine. It's gone. Maybe because they are too popular and they are kind of scrubbed away by the popular terms. So based on the terms of these 10 topics, these are the description of the topics. And in one of the homework, you will do the same exercise by using the by using the top terms of the topics, you will interpret the topic and try to describe it with very simple language. Let's take an example here. I think number 6 is very distinctive because we're in Texas. Taco, chip, salsa, Mexican, tortilla, queso. There's no other interpretation. I think you will come to the conclusion that this is Mexican cuisine. This topic is all about Mexican food and Mexican style restaurants. So that's the end of it. I think this exercise is quite interesting. I don't know what you think. Okay, any questions? No questions? Let's call it a day. Agreed? Okay, so I'll remain here. Feel free to leave and have a nice Thanksgiving. Avoid gatherings, be serious about your health. And I will be worried about you if you do recklessly. I still wish to see you after Thanksgiving in the final exam, right? Okay, if you have any questions about the homework, let me know before Thanksgiving. It's due before Thanksgiving.
Professor, I have a question about my homework.
Yeah.
For question 5, let me double check.
Feel free to leave if you don't have questions.
So, can I make sure for question 5? So when I asking for the TF, like transform to the
right
NumPy data, so it's a academic, but it's a column abstract prepared, right?
Yes.
Okay.
Yeah.
And I tried to, because I use a Advanced Canada. And
use what?
I use Anaconda for the Python.
Okay. Use Anaconda. Okay.
Yes. I'm not available to pipe install pattern.
Oh, you can't install pattern. That's fine because for the homework you don't have to install pattern. You need to use pattern when you want to go through and follow everything in the demo.
So can I
think you can skip those part of the demo and go direct. And also you use pattern to prepare the data, but the data is already prepared, right? So you don't have to do that for the homework.
Yeah, but I cannot run can I still run LDA analysis?
Yeah, LDA is part of the scikit-learn. As long as you have scikit-learn, you can do that.
Okay, that's all my question. Thank you.
Right, sure. Any other questions?
Professor,
Yeah.
I was trying to follow along with the demo tonight, and when I run the code, I somehow got empty result.
Okay, which part? Which part? Which part did you start to get weird results?
Like starting from, I was trying to rerun the code all over again, and like somewhere near the LDA analysis.
Okay, we need to be very specific because some of these codes maybe were left there unintentionally. So that may have changed some part of the data that later, but you didn't get exception, you just get empty result?
Yes, I just got empty. Like it was supposed to return some text values, print something, but I just got nothing.
So okay, but you didn't change anything, right?
No, I didn't change anything. I just rerun the code from from the very beginning.
So that may, okay, because I put together this over 3 weeks. There may be something in the beginning that may not make sense anymore and may change something that will cause a problem later. I would suggest that you run the code from, so there's a table of contents, right? You run the code, you first you run the import packages, the 2 cells, and then you can skip a few parts all the way and go all the way to learn to prepare texts.
Okay.
Right. And then run from there. Then it should be fine.
Okay, thank you.
But avoid running even beginning from learn to prepare, that section, avoid running everything in one try, because there are at least 2 parts of these operations that runs for a long time. Some run 2 minutes, some run 1 minute. It's better to monitor the progress a little bit more, and examine the results in the middle before you run those long results. You can see how much time it ran, right? The output was retained before you run the cell, so you get a sense of how long that will take. I use codes to keep track of the how long it ran.
Yes, I can see them in the original demo file, but after I run the code, they just disappear.
Yeah, so that's what happened. Also, you may have an issue when you skip some of the parts in the middle, because one cell under the pre-processed section depends on something that you have run earlier. But in my version, I've already corrected, but I haven't corrected in the version on Blackboard. So do you have the Jupyter Notebook open?
Yes.
Yeah, so you can do this by quickly fixing this by copy a part of the codes to a place, then you can solve that problem. Let me share my screen with you. And you will know what I mean. So this part, can you see it?
Yes, I can see it.
Right. So in the table of content, go to this section, scroll down. Right, scroll down all the way to integrate all, and copy these lines. Copy these lines up until pre-processed. Copy these, all of these. Let me know if you're done.
I'm sorry, I couldn't find this part.
So you can search in website. I mean, you can search on web page, demo : space integrate all the above, and you should be able to find it.
Yes, I found it.
Right. So copy the first 6-7 lines all the way until this list, the end of the list. Leave 2 lines.
Yes.
Leave 2 lines out and copy. And then go down all the way to pre-process, prepare the column using pipeline. In your version, I think you only have these.
Yes, I only have.
So you want to paste whatever is copied over here. And after doing these, then the next time you open this Jupyter notebook, you will need to run these two, right? Because this is pandas, it's not imported later. Pandas and NumPy, as well as a random seed. So after running these, you can go directly to clean and prepare and run everything below. You know, you can run from this part all the way until the cell that you pasted values, all the way until here. You can run it in a second. And then this cell requires 2 minutes. Close to 2 minutes, 2 minutes on my laptop will be similar to yours. So you want to run this alone, you know, instead of running this as part of a big batch. Run this and make sure there's no problem. And run this and run this. This is sanity check. Make sure that you get a healthy, you know, looking output. Then you can run these several cells in one batch. They are quick all the way until but these are empty. These are without any answers in it, so these won't run. So you can't run the entire document in a batch because it will stop here. And then resume here. This cell will also take a minute or two or so, right? And afterwards, everything can be run very quickly. Okay.
Okay,
That's
thank
it.
you so much.
Yeah. Mm-hmm. Anything else? Any other questions?
I do have a question for another class, if you don't mind.
Which class?
For MIS, the projects.
Oh.
The predictive.
Okay. The other class. Okay, I see. Yeah. What's your question?
Okay, so we are doing the EDA part. So I'm confused, like, because we need to transfer the variable. So if the variable is a normal distribution, it should be good for us. But how about it's like not normal distribution? Should we normal?
Now normal distribution, it's you don't have to do it. It's not something that will definitely help you in terms of performance. If you want to be really experimental, you can try different things and, you know, and compare. But if you don't have enough time, you can argue that that professor said that, as the professor said in class, that fixing the normal distribution doesn't always help the predictive results, right? It could even make the model worse. It could happen, yeah. So it's a case-by-case scenario. So you can, I think you can say that, you know, to be conservative, you did not take the log transformation. You did not change the distribution, the normality of the data, just to be safe.
Okay.
Yeah.
For the binding parts, can we do
Binning?
like yes? Oh, I'm sorry, binning.
Yeah.
So the binning should be before the model process, right?
Yeah. Binning is part of the preparation. Or binning is part of the EDA.
Okay, so the EDA you mean is a before the graph or like the after graph?
So EDA is if you want to keep every section clean, then it's the context, the problem, and importing data. Then you can start doing EDA, or your EDA before the stats explore. After the basic statistics, you can do EDA. After doing all the EDA, you can conclude from EDA that these are the things that need to be considered
Fixed.
in a model, and as well as fixed and transformed in this way, then you can prepare the data. This is data preparation phase. And after preparing the data, you can proceed to modeling. Yeah, and data preparation also includes the partition.
Okay, so the EDA is just like we are kind of understanding the variables and giving some ideas. Okay.
Yeah, and identifying some issues.
For some issue.
Right.
Okay, I see. Okay, thank you.
Great, sure. All right, so we're going to say goodbye, good night.
I have one question.
Okay, go ahead.
So it's related to the project.
Right.
So I've been going through the project. So, just a small doubt. I wanted to know clearly what are your expectations, Professor? Things like, so one doubt is, should I build on multiple models? Should I use logistic regression and then use multi-layer perceptron, compare the accuracy, or just go with build a basic multi-layer perceptron with stochastic gradient descent, then change the optimizer, then include regularization, and then change the activation functions. So what do you want me to do? What is the way you want me to choose?
So the basic objective is, okay, there are two parts of the evaluation of the work. One part is for me to see whether or not you are comfortable with the several, I mean, whether or not you identify the objective clearly. The objective is the prediction part, to predict, what is it that's being predicted, how is the model serving that purpose, and in achieving that goal, that goal is clear. You want a model that is highly accurate, right? But because of the noise in the data, because of limitations, models will have different levels of achievement. So you will try to improve it by making proper selections and tweaks, or it could be regularization or reducing the regularization. How do you improve the model based on these evaluation results? That's part of my evaluation. Does is what you do reasonable? Are you applying? Are you comfortable with dealing with these challenges and situations? When you try to improve the model performance, what do you prioritize? So all of these, there's no single correct answer in my mind. Does that make sense?
Yes, sir.
Right. So I'm looking at the thought process as reflected by the work, but ultimately, one can work very hard, but end up pursuing a goal that is not reasonable. That could be, it's kind of taking something too far, and in pursuing the accuracy too far without considering the false positives, false negatives, that would be something I will look out for.
Right.
Yeah.
And one more thing, do you have to construct a multi-layer perceptron from scratch, or can I use Keras?
Oh yeah, no, I would suggest that you use the packages.
Okay, right. Thank you very much.
Right.
And last doubt. So there are basically two data sets. One is Insurance 3 training and Insurance 3 score.
Right.
So if I'm right, the score, I'm going to use score for predicting, right? So,
right.
And I'm going to use training data set to train and split and.
Right.
Yeah.
Right.
That's it. Yes, sir.
Yeah. So it's like a competition, but it's more than that. It's a pedagogy purpose, right? but the process is like a competition.
Yeah.
All
Thanks
right.
so much, Professor. Yeah.
Yeah, sure. Yeah. Stay well. Enjoy your break.
Yes, sir. Happy Thanksgiving.
Yeah, you too.
See you soon.
Bye.